morning all of you. Yesterday we were looking into the von Karman-Polhausen solution for heat transfer problem. Just want to make a small correction. Probably when we looked into the solution for zeta, so we had the lambda value for the stagnation region as 7.052 and the resulting expression for zeta so we had to solve this ODE, and the solution as a combination of the homogeneous and the non-homogeneous parts came out 0.6699 by Prandtl number. Okay, so you can look at the non-homogeneous part is actually basically a constant, so that's why we know the particular integral has to be a constant. Okay, if it is a function of x in any form, then we have to assume that particular form and you have to calculate the particular integral. And coming to this particular equation now, this is for the case where we have flow past a circular cylinder. You have the heated circular cylinder, okay, and this is the stagnation value of lambda, which corresponds to 7.052. so now at x is equal to 0, so this is where you are starting your x, okay. So you should be careful that the boundary layer thickness is actually not 0, okay, because the stagnation flow comes ahead and then it basically bifurcates like this. So you have a certain value of boundary layer thickness, and the same thing holds true for your thermal boundary layer thickness also. So you have to be careful when we stated that at x is equal to 0, we came to the conclusion that the constant is 0, essentially because of the fact as x tends towards 0, the solution will go to infinity, okay, because this is a negative power. Okay. So in order to make this value of delta t, that is the thermal boundary layer thickness, finite at x is equal to 0, this constant has to go to 0. Okay, so this is why we put this constant as a, probably I didn't explain it very carefully. So you have to be careful that at the stagnation region both the thermal boundary layer thickness and the momentum boundary layer thickness are both non-zero, okay, and therefore in order to give a finite value of delta t, so your constant has to be 0. That's why the final solution was cube is equal to 0.6699 by Prandtl number, and from this we have calculated the expression for Nusselt number. Okay, so this is, I just want to clarify before we proceed further. Today we will introduce a smaller approximation to the entire approximate method, and this is also called as Walz approximation. Some people also refer this to as Thwaites approximation. I am not sure why this is attributed to two people. I don't know the historical reason, but some books, some of the more recent books, they refer this to Walz approximation, and some of the earlier books they refer this to as Thwaites approximation. And what essentially happened is this person Walz, he pointed out that we had defined this function h of k, right, so a complex function which was function of f1, f2, k and so on. So he said, and we were thinking that we can construct a lookup table where we will change the values of lambda. For different values of lambda we will plot f1, f2, and therefore we can plot h. So he said when he did this plotting, we found this h of k was actually a linear function of k, okay. So and he got a curve fit of a straight line which was 0.47 minus 6k. So he just simply plotted h of k as a function of k at k equal to 0, this was like 0.47, and then it was decreasing like this. Okay, so this was a very good news, because now since this is a linear relationship, we can simply directly use this to calculate z. Okay, so we know the expression for the momentum, reduced momentum integral equation, which was dz by dx is equal to h of k by u infinity. So this was the expression that we derived after we substituted those velocity, approximate velocity profiles. Finally, what is your z? Del 2 square by nu. So this is nothing but a parameter which involves the momentum thickness. Okay, so this has to be solved in order to get new values of z, and then we found from there you iteratively solve for new values of lambda, and keep doing this as you keep marching from one region to the other region till it separates. Okay, now this was because we didn't know a very good functional relationship for h of k. So now when Walz plotted h of k as a function of k, we found this is nothing but you can fit it very nicely with a linear line, and therefore a linear approximation was derived. Now we will substitute this into this expression. So this will be 0.47 minus 6k by u infinity. Okay, so this is called the Walz approximation. The rest of the thing is, it is just how do we now simplify this equation. Now directly we have dz by dx is equal to this, we can integrate it out. So one more step, we can write this as u infinity dz by dx is equal to 0.47. Anybody remember what k is? Z into du infinity by dx. Okay, this is coming essentially from the pressure gradient parameter. Okay, z into du infinity by dx, right? So therefore this is a function of k is nothing but basically a function of z. Okay, so it's wiser to put this in terms of z du infinity by dx. Now you see we have an equation directly for z, okay, which we can integrate it out. We can also rearrange this as u infinity power 6 delta 2 square by nu. So I am going to substitute my z as delta 2 square by nu. So this can be rearranged in this manner, 0.47 u infinity power 5. Okay, so now you can expand and check. So this will be the same. So you have nu is a constant which can be taken out. So you have d by dx 1 by nu. So we can take delta 2 square and u infinity. So this will be 6 into u infinity power 5 du infinity by dx, plus I have u infinity power 6, okay, 2 delta 2 into t delta 2 by dx is equal to 0.47 u infinity power 5. Okay, so I have 6, and now my z is nothing but nu square, delta 2 square by nu. I have this, so I can divide throughout by u infinity power 5. So this will give me delta 2 square by nu du infinity, this is 6 du infinity by dx, plus u infinity to delta 2 d delta 2 by dx is equal to 0.47. So this is u infinity, so this is 6z du infinity by dx, and I have u infinity, yeah, so this dz by dx is nothing but 2 delta 2 into d delta 2 by dx, that is equal to 1. So therefore you can, all this can be combined into one neat way of clubbing together this particular term, and this will be nothing but the expanded version of this. Okay. So now with this we can we have an expression directly in terms of delta 2 which we can integrate it out. Okay. So if you integrate it, so integrating, so we can say delta 2 square is equal to 0.47 nu by u infinity power 6 of x. Okay. And so I am going to integrate the right hand side, which will be 0 to x u infinity to the power 5 of some z dz. Okay. So this is my final expression that I now get. So I simply integrate both sides. Okay. And just I write this in terms of delta 2 square. So therefore I will call this as number 1. So your earlier expression for solving for z, in fact that is solving for delta 2, was doing numerically. You have to solve this ODE numerically. Now once you introduce this linear slope approximation, okay, constant slope approximation into this, and you directly integrate it out, you get a simpler integral. Okay. If your function is known, u infinity, you substitute here, you directly integrate it out, and you can get an expression for delta 2 right away. So there is no numerical work involved in this. Okay. Although this is an approximation, nevertheless it is a very good approximation. In fact I can give one homework where you can check this, whether this linear approximation is valid. Okay. You can calculate h for different values of k and plot and check for yourself. Alright. So this is the thing, and here we have used the fact, of course when you integrate it out you have a constant here, constant of integration. Okay. So now at basically x is equal to 0, when you are integrating this with respect to x is equal to 0, your u infinity that you are using, so this entire term has to be 0, because at the stagnation point your free stream velocity is 0. So therefore this entire term will be 0, therefore the constant will be 0. Okay. So we have used that at x is equal to 0, your u infinity power 6 delta 2 square by nu equal to 0. Okay. So it is not that your boundary layer thickness is 0, but your u infinity is 0, which leads to this particular conclusion that the constant is 0. So therefore this is the final expression. Okay. Now we will apply this again for the cylinder problem. Earlier I had given you the algorithm to solve for the cylinder case in a more rigorous way, solving the ODE numerically. Okay. So first we will look at the cylinder problem near the stagnation region. So if you substitute the profile of for u infinity, your u infinity is basically 2 v infinity r naught by x by r naught. Okay. So if you substitute this and you integrate it out, you get delta 2 square is equal to 0.235 into nu into r naught divided by v infinity x power 6. Okay. So this is basically 0.47 divided by 2, and you have v infinity x power 6. Okay. That is u infinity power 6. Actually everything is power 6, but inside the integral also, when you substitute for u infinity to the power 5, the extra terms cancel out. So you have z power 5 dz is what is left out inside. Okay. So you are basically substituting for u infinity, here u infinity power 6, here u infinity power 5. So you have 2 v infinity by r naught, which is the same. Okay. So then you will be left with the factor that this is V infinity into V infinity divided by R naught. Here you will have x power 6, here you will have z power 5. So this you can integrate out directly. So this will be point. So if you integrate this, this will be nothing but x power 6 by 6. Okay, so 0.235 divided by 6 will be 0.0391, and so x power 6 cancels. So you have nu R naught by V infinity. Okay, so therefore there you go, you directly have got an expression for the momentum thickness without solving the ODE rigorously. You know, near the stagnation point directly you find it. Okay, and you can also calculate the value of lambda. For doing that, we need to estimate the boundary layer thickness, which is estimated. So how do you estimate the boundary layer thickness? Delta square. There is an expression because delta is a function of lambda. Lambda. Okay, what is the original expression? How did we define delta? Lambda nu by du infinity by dx, right? So we defined this parameter lambda like this. Okay, so delta square du infinity by dx by nu, is that right? Okay, so therefore for this particular case we can substitute du infinity by dx, which is nothing but a constant 2v infinity by r naught, and that comes out to be lambda by 2 into nu r naught by v infinity. Okay, so now we know lambda delta as a function of lambda. Okay, we have an expression for delta 2, so we can calculate the ratio of delta 2 by delta the whole square. So you let me know what this expression will be. So if you take the ratio of these two, v r naught by v infinity will be cancelled out. Okay, this will be 0.0391 into 2 by lambda, which is 0.0782. What we are trying to do is we are trying to solve for lambda. Okay, so delta is a function of lambda, and we have an expression for now delta 2 by delta the whole square, which is now a function of lambda. We also have derived delta 2 by delta square. We have expressed this as another function of lambda. Do you remember that originally? That is 1 by 63 square 37 by 5 minus lambda by 15, or you can say that this is equal to square root of this, and then you can write like this, lambda square by 144. Okay, all right. So now we have a expression, algebraic equation in terms of lambda. Since delta 2 by delta is originally this in terms of lambda, okay, now we have another expression for this particular problem which is like this. So we can equate both and you can find out lambda. If you do that, in fact this has to be also solved iteratively, so lambda will come out as 7.25. okay, now you can compare this with the lambda that we got earlier, that was 7.05, right? So it's slightly off, but nevertheless it's very close. Okay, so I think this is now much easier to solve than the earlier case. What we will do is now go ahead and complete the heat transfer solution. So for the heat transfer problem, whatever we have derived, we have assumed a cubic polynomial, and then we have substituted into the energy integral, and we have finally calculated the expression for zeta, which is the ratio of delta t by delta as point, this is zeta q, this is 0.6699 by Prandtl number, right. So the same expression is valid, because as far as the energy integral is concerned, all you are doing is you are substituting the velocity profile, approximate velocity profile, approximate temperature profile, and finally you have expression in terms of zeta which you are getting the solution for. Okay, now when you are getting the solution, you have substituted a value of lambda there. Okay, the original expression was something like this. So your expression was zeta d by dx x zeta square root of lambda 12 plus is equal to 90. Up till here everything is the same. Okay, so this is coming from substituting into the energy integral, right, for the velocity profile and the temperature profile, and simplifying a little bit where we are neglecting all the higher order terms of zeta and only zeta square comes finally. So now from here we should use the particular value of lambda which we got from the Walz approximation. Okay, so that is basically 7.25 instead of 7.05 which we substituted earlier. If you do that, earlier you got your zeta as 0.75875 by PR to the power 1 by 3. Now with this you will be getting zeta as 0.864 by PR power 1 by 3. So only the constant will change a little bit, because now your lambda is slightly different. If you substitute it, your solution for zeta will be just slightly differing by constant, it will be 0.864 by PR power 1 by 3. So that is it. So once your zeta is determined, you can calculate your heat transfer coefficient and your Nusselt number. Okay, so we know that the heat transfer coefficient is 3 by 2 k by zeta delta. Okay, so the expression for delta is the same for both the Walz approximation and the original von Karman-Polhausen solution. So only the value of zeta is differing slightly. If you substitute this, you will be getting an expression for H which is like 0.645 k by R naught into Prandtl number power 1/3 RE power half. Okay, now if you define your Nusselt number as H into D naught by K, okay, so this will be what, 1.29 Prandtl number power 1/3 RE power half. Okay, where your RE is nothing but V infinity D naught by mu. So compare this with the expression that we obtained yesterday. You remember that expression when we used lambda 7.05, what was the expression that we got? 1.1. No, that is the exact solution. 1.291, correct. Okay, so this is 1.29. So finally, in terms of Nusselt number, there is hardly any difference. Okay, whether you use the Walz approximation or not. So that's it. I see, this is to just give a good idea that Walz approximation is pretty good, especially in terms of the heat transfer calculation. You get a very good agreement with your Polhausen's solution, as well as your exact solution is what, 1.145, and that has Prandtl number 0.4 dependent. So there is some difference between the exact similarity solution and the approximate solution, but using Thwaites approximation or Walz approximation is much more judicious, you get faster solutions than solving the ODE. Now the same problem where you are looking at circular cylinder can be done by using Walz approximation, right? Okay, so the same way you take the profile, the complete profile u infinity of x is equal to 2v infinity sine x by r naught where your x is equal to r naught theta. Right, you take your full profile which is coming from the potential flow for describing the free stream velocity for circular cylinder, and that can be substituted into this, okay, expression number 1 right here. So that u infinity can be substituted. Now you can integrate it. Now you have to be careful when you integrate it, you are integrating sine power 5 x by r naught there, okay. So in the stagnation region you have made the approximation that for small values of x by r naught sine x by r naught is equal to x by r naught, but if you are looking at integrating for the entire flow from the stagnation point till the separation point, you have to use this profile as it is, okay. And when you put this profile, you have sine power 5 term here, sine power 6 term. So if you are finding it difficult to integrate manually, you can use some numerical technique such as trapezoidal rule for integration. Simple trapezoidal rule or even simple rectangular rule will work. So you have to start from some point right here. So at this point you know the value of delta 2, that's what you have determined, okay. You also know the value of lambda and everything, so you can start from that point 0 to some point next, okay. So you can keep on integrating that way, okay, till any x that you want, till you go to separation, okay. For each point that you go, so now you calculate the new value of delta 2 square, and therefore you can calculate the new value of lambda like this, because you know the ratio of delta 2 by delta, correct. For each value of x, you know the new value of delta 2 by delta, you also know the original form, original relationship, you can equate those two and solve for lambda, so that will give you a solution for lambda basically, okay. So this you keep doing till you hit separation point where your lambda becomes equal to minus 12. So now this is a little bit more easier, you can do this on an Excel sheet, you do not have to program it. So you can simply do numerical integration and you can solve this equation also, you can find roots of this in an Excel sheet itself. So that will give you again the boundary layer thickness and the momentum thickness and also the separation point. So everything can be obtained from the Walz approximation, okay, and this will be nearly as good as doing it by the solution, numerical solution to the OD, okay. So in fact I will give the next assignment, which will be assignment 3, which will include all the integral solution problems. I will also ask you to do this for circular cylinder and see for yourself how you can basically find the separation point and get expression for boundary layer thickness, momentum thickness, okay. So same thing can be done for any wedge problem, the Falkner scan solutions where you had assumed some kind of a wedge flow and a velocity profile of this particular sort. Now you can apply the Walz approximation, you can substitute for u infinity here, you can integrate it out, okay, and finally you can calculate the value of lambda, and from there of course your boundary layer thickness, and again you can use that into the heat transfer problem where you substitute the expression for delta and the particular value of lambda you calculated you can derive the expression for Nusselt number. So you can do this for any value of m, okay, like the way you did your similarity solution, you can do this and you can compare the result with the similarity solution. You will find the agreement once again is pretty good. Okay, so any problem with pressure gradient can be handled with the Walz approximation. Okay, so probably I will stop here, but I will probably will have some kind of a small discussion if you have any doubts, because I have one more last topic left under integral method, which is non-uniform temperature boundary condition. So far we have assumed that the entire plate is heated with a uniform temperature or uniform heat flux. In most of the cases that is not true, okay, the profile will be varying. So what happens if you have a variable temperature profile? Okay, so we cannot do with the similarity solution this kind of a problem. Of course you can use similarity solution if it varies only linearly, but if it is any other variation you have to do integral solution. So we will see for a flat plate case what is the technique to how to introduce a non-uniform temperature boundary condition, how do we solve this. Okay, so that will be the last topic. I will take that about a couple of hours next week before your quiz 1. Okay, so quiz 1 will have all the topics till your integral solutions. So pretty much any doubts that you have in this, I hope you understood the Walz approximation, because you will be now using this to solve this flow path circular cylinder. Okay, so if you have any questions you please ask me. Is it clear? You have understood? Huh? This is just a dummy variable. Yeah, this is just a dummy variable. You can, if you are having say cx power m, this will be c zeta power m. So that will be just a dummy variable, and it indicates that whatever upper limit till where you are interested to integrate, so that will be used into the dummy variable. Okay, so earlier x indicated some arbitrary location. Now when you are integrating it you have to use the dummy variable, because you should not confuse this with the limit of integration. Okay, so many a times we use the same thing, but we know that we should use the upper limit, but to differentiate it clearly, strictly speaking, you always have to use a dummy variable. Okay, so you are clear with all of this, like how to calculate your delta 2 numerically and all that. You have to numerically integrate it by trapezoidal rule. You can start from say the stagnation point. Okay, assume this is a trapezoid between these two. So you can, if you are integrating to the first point, it is just only one step. If you are integrating somewhere till somewhere here, you have to assume many trapezoids and sum them all together. So the area under each trapezoid, sum them all the trapezoids together will give you the area under the integral, basically. So that is the approximation that we are. So at each location, so you calculate the value of delta 2, and so like this you will have an expression for delta 2. Right now we have completely, there is no dependence on x here. Okay, so there when you are putting a sign profile, there it will have a dependence on particular value of x. So for that particular value of x you will have a particular constant, okay, for delta 2. Okay, so and then you, now this is so this is the expression for delta 2, this expression for delta will be there. This is again a function of the position, because we are now differentiating sign profile. Okay, so there will be a x dependence. So for each position the value of delta 2 and delta will be different, and that you take the ratio, so you will be getting an expression in terms of lambda. Okay, only this constant will keep changing for each location, and then you can solve this, find roots of this, okay, get the new value of lambda, and you know that where the region is, as and when the lambda keeps going negative and increasingly negative, you know that you are approaching close to the separation point, and and then you keep doing this integral till where at a particular point where lambda becomes minus 12, and then you know that you have hit the separation. Okay, so all this can be done in a Excel sheet, you don't have to write any program for that separately.